and maybe it's only in the way in my office.
Yeah, we don't see a taskbar. We just see your slides right now.
It's like APL, a programming language, and so
that's
on.
what we say.
Okay. So I put in these pictures because they, probably because they came from another slideshow, but they refer to some DNA identification tasks that I've gone through. This is my website, but maybe better than that. Oh, by the way, Rohan, how much time did we budget? Was it a full hour or was it more like 40 minutes? I don't know.
Yeah, we have a full hour for you. So however you want to split that in terms of like talking and answering questions is fine.
Okay, I'll just keep my eye on the clock anyway. So I put in this slide so that if you want, you can get my PowerPoint. I've uploaded it to my website. If you search for forensic mathematics, that might be an easier way to get to my website than to remember the URL. And on the opening page, you'll find a link to a page that has a lot of presentations that I've given. And toward the bottom of that page, you'll find this conference. Okay. Let me start out with the beginning of my experience with computing, and I hope I don't forget to do some name dropping as invited to do so by Rohan. Okay, so well, computing started in 1822, you could say, and I hope you all know who Charles Babbage is, but he's not part of this story. You certainly know who Alan Turing is, who had a big influence in inventing the idea of a computer, but I never knew him. I did happen to see an ENIAC when I was maybe in 5th grade in 1955, but and I tried to get into a conversation about it, but there was misunderstanding and I never learned anything about it. But that was one of the early computers that took up an entire big room. This was a most interesting experience, and this is where I learned about computers. I think I was, I guess, a junior in high school, and we had this once a week lecture club or science club, which would start with a plenary lecture by some eminent scientist in the neighborhood, which there were a lot of, even though this was before that neighborhood got the name of Silicon Valley. But that's what it was. Now it's Silicon Valley. I went to high school in Palo Alto and across the street from Stanford. So Professor Forsyth was a math professor at Stanford, and he came over and he gave us an incredible talk, which was the first that I ever heard about computers, I think. No, not the first I'd heard of ENIAC, but the first I learned anything about them. And here's what he did. He made a computer in front of our very eyes, and the components were made of human flesh. So he designated about 15 or 20 of the students to be computer components, mostly gates. I don't know if everybody knows what a gate is, but it's essentially an atomic component of a computer. And a gate can be, for example, an AND gate. An AND gate has wires in it from 2 other sources, and it outputs a current only if it has current coming in on both wires. So Forsyth told the AND gate people who they should be watching, which other people they watch. And he says, so when the people watching, both of them have their hands up, then the next time I call cycle, you should put your hand up. And also some people were OR gates. And some people would be registers, I guess, something, I don't remember the right word, somebody that would hold the numbers. And so in this way, he built a 2-bit adder So you could add any two numbers as long as the sum was no greater than 3. And of course, it was binary. And so he put in an addition problem of 1 and 1 in 2 registers. And then he started saying cycle, and hands went up and hands went down. And after 2 or 3 minutes, he said, there's something wrong here. There's a faulty component. And I don't think this was planted. He did have a son who maybe was in the room. His son was a friend of mine. But it seemed to me that he just realized that one of the kids was not doing his job right. So he said, I'll have to replace the part. So he told that kid to go back in the back of the room, sit down, and replace that kid with another component. And then he said, cycle, cycle, cycle. And after some time, we learned that 1 + 1 is 2. So I was impressed by his diagnosis, and I was intrigued by computers from there on. And as it happened, Stanford had a computer, a total of 1 computer, an IBM 650, not nearly as big as the ENIAC, roughly comparable to a rather bulky refrigerator, plus a card reading unit that was like a very large horizontal freezer. And I was able to sign up for time roughly once a week, I think. I don't remember exactly. And I could write little programs and test them out, or I could play 3D tic-tac-toe using a program that had been written at Bell Labs, which I thought it was quite amazing that they wrote a program which was certainly better at the game than anybody I ever met until many years later. When I wrote a program in those days, it was in raw decimal. The IBM 650 was a decimal machine, as the early computers tended to be. It wasn't until much later that people caught onto the idea that binary is worth the price. The price being that it doesn't work very well for currency. Okay, APL, the programming language APL stands for a programming language, and that was not intended as a joke. It was the actual name of the book that Kenneth Iverson wrote in, I think, 1958, when he was an associate professor or something like that at his alma mater, which was Harvard. And he was a very interesting guy. But first of all, as you might imagine, his bent was to write a mathematical notation, and that's what he did. And as I recall it, he didn't do it with a particular idea of a programming language. I mean, for computers, more it was a matter of for algorithms. So the first major project that I was aware of was he and his colleagues used APL to describe in excruciating detail exactly how the IBM computer of the day worked, down to the level of the circuits. In other words, exactly how the computer does floating point multiplication, for example. And a good friend of mine from Stanford came to Ken's attention. This would be Larry Breed, because Larry proofread Ken's article about how the IBM 360 works, found some errors, confronted Ken with them when he had a chance to meet. And Ken, of course, swore. I don't remember if the word he used was damn or fuck, but let's use, as I recall the phrase, he would refer to fucking Breed, but in a sense of love. He said we should have found him earlier. And Larry, when I graduated, invited me to spend a summer at IBM working with him and with Ken. So that was terrific. Ken was a very smart guy, very opinionated, And Larry was extremely, well, he was, I can't explain him and you don't know him, but he certainly taught me about, you mentored me, let me put it that way. I never thought of the word, but he taught me how to look at things in great detail. And I did a bit of APL development on the early system that we had at IBM in those days. Now I'll tell you a tiny bit about APL. Now, I think the first Ken used the syntax A plus B, a plus sign with operands left and right, as the standard for what he called dyadic functions. And another dyadic function would be A min B. So he wasn't thinking so much of the modern method where you have a function name followed by an arbitrary number of arguments, although the APL that I use today does permit that. And there were something like 23 binary operations as opposed to the handful that is classically listed in computer languages, even though I guess mathematics has more. In other words, not just plus, minus, times, divide, and exponentiation. And therefore, the what at least used to be standard in programming languages, the precedence rules, like exponentiation binds more strongly than multiplication and division, which bind more strongly than add and subtract. That's really hopeless, a hopeless pattern to try to advance when you have 23 of these plus ones that you can write yourself. So he simplified that, and everything has the same precedence. It's just right to left. Also, we have monadic functions, of which minus would be the paradigm. But you can also say, we can use the minimum symbol in a monadic sense to truncate, so that the the truncate of 3.2 would be 3. And you might have noticed that originally mathematics used square braces for truncate. But perhaps because of Ken's influence, this thing is now used in mathematics. And just like APL, they'll put the little horizontal dealie on the top if you want to round upward. However, they do use two symbols on left and right. They don't fall for this just leading function business. Oh, okay, I already told you that I think this is the case. Nowadays, besides the APL manufacturer that I've been working with for quite a few years now, there are a few others, which is great for keeping things alive and different groups of people thinking of different improvements. But it's slightly disadvantageous in that there's no clear-cut uniform standard for APL. They're very similar, and the differences are sort of maybe obscure generally, but they can bite you. So if you switch, you have to learn some obscure difficulties. As I mentioned, I did some APL development with Ken and Larry in the 60s, and had an opportunity a little bit more recently to do some of it. But I'm not an expert in that stuff anymore. I sort of can follow what's going on, but I'm not at the forefront of technology by any means. Somewhere along the way, I started using programming skills as a way of making a living. And then I got lucky and found something much more interesting than just picking up whatever random offers for programming lay on the streets, like doing insurance analysis for hospitals. That's terrible. But DNA identification, which everybody loves, especially programmers and statisticians. So I'll talk about that a little bit. There's a company called Dialog APL, which I think are headquartered a bit, rather near Oxford in England, but also offices in Elsinore, a bit north of Copenhagen, and that's where the owners actually live. Now, they'll let you use it for free, and I think you don't even have to sign up. Just go to the website and you can use the demo for free. There are various kinds of tutorial pages, including a page that I guess is a de rigueur thing for programming languages that lets you practice right on the web by typing things in and paying attention to what they tell you. They've got it running on quite a few platforms. I use a PC and I don't know much about Macs. You may be aware of Raspberry Pis. I understand that they're very cheap and really work. So that's interesting. And when I say nearly Android, I enjoy going to the Dialog conferences yearly. There's one in about a week in Portugal. And the people there are very stimulating developers, very interesting. And one of them gave a talk a few years ago in which he showed that he had a pilot version of APL running on his Android watch and his Android phone. As a parenthetical, among the things that are important in deciding whether a programming language is good for your use, there's some not obvious kind of non-technical considerations that I think are important. There can be clumsy things about the language, for example, but if the programmer interface is very good, like it has a good debugger, and like it has other tiny things that just make it easy to write programs, that's a big deal. If it has a forum where you can get insight from talking to other people, that's great. And and service. In my case, for example, I appreciate a lot that I can ask any question I want from an expert at Dialog, and they answer me at a high level. I don't know how that works for other people. In my hands, and many people, it's a very efficient development platform. The fact that and in part that starts from the fact that it's so concise that you can get a lot of APL into a short amount of text. And my guess is that's important partly because it reflects a mathematical and consistent design, but it's also because you can keep track of things. So short programs have these obvious advantages in that respect. And I have a quote. I've been trying to remember this guy's name. I had a part-time job my last undergraduate year in college. And as was often the case in those days, the experts in computing were not people with a computer science degree. In fact, there was virtually nobody with a computer science degree. Professor Forsythe, who I mentioned earlier, initiated that department at Stanford. And he was a pioneer, so there weren't many people even that had that opportunity. My boss at Lockheed was in fact an English major. And I remember another English major, or something very close to it, who was Ken Iverson's closest colleague at IBM when I was there, Eugene McDonnell. Anyway, I claim that I can I found I program fast. I don't know how much it's APL and how much it's my understanding of how to use it and how much it's just my mathematical ability. But this is important. And another point is, well, I'll get to this, so I'll move along according to my slides. So some negatives. I showed you already some funny symbols that you don't have on the normal keyboard. So that means to use APL, you have to learn to use, to type in some things that take control into control shift, quite a few of them. And also APL has their own idiosyncratic notations for things. Well, this is the mathematical thing. The or symbol, rain or sun, means you means that the arguments are 0 and 1. 0 and 1 are stand for truth and falsity, falsity and truth. They could be vectors. So rain could be 0, 1, 1, 0, and sun could be a similar vector of zeros and ones. And we also use the mathematical symbol for and, which means that we can't use it for exponentiation like is typical in computing contexts. And for multiplication, we don't use a star. We use real multiplication symbol, which exists in the Unicode character set. But that does mean that we're not using this symbol that's actually part of the keyboard. We use this symbol for exponentiation. And also, cleverly, all these things have dual use. If you don't say what the base is, it's E. So as a monadic, star 10 means E to the 10. APL is not that well known, but maybe compared to and that's a disadvantage in various ways. It means there's not so many people you can work with or get help from. But it does have kind of a odd advantage. I don't have to be so careful to obscure the code when I'm selling software to people. In practice, I trust my clients, but anyway, they would have a hard time stealing my code. Now, there's a lot of fun in APL. Things that make it efficient, for example, it's an array language in that generally you certainly can say 5 plus 7, but as often as not, you were dealing with a bunch of numbers at a time. That's why we have, that's why programming languages have loops. I don't know why this thing is skipping ahead. I'm not good at this. So an object 1, 2, 10, 12 can be stored in a variable name. And incidentally, you don't need to declare which variables you're going to use or which ones are integers and so on. So this is a 4-element array of numbers. This is a 4-element array of letters. If you want to add, you add everything on the left, everything on the right, and there's a special rule for singletons that they apply to everything on the other side. Here's a couple of funny symbols. Iota means create a list of numbers from a list of 8 numbers, starting with the first number, which could be 0 or 1, depending on how you what settings you use. This symbol reverses, so we have 8, 7, 6, 5, and so on. R is row. I don't know why it was chosen for the shape of something, but this says that we turn that string of 8 things into a 2 by 4 array. So what you get is this picture. A very important elaboration of this stuff is that you can nest arrays. So you don't just have arrays, you have trees. You put an enclosed, sometimes, depending on context, you can put an enclosed symbol before something to make a string into a single item. And then you would be able to write things like this. Because of the parentheses, this first thing is a string also. So this is a 2-element object of a 4 and a 3-element object. And you can nest as deeply as you like. It's very useful, up to at least a handful depth. Indexing, well, you can index in the same way that most languages do. But if you think of it, that's really kind of a bastard notation. It's not consistent with writing functions. So APL vendors eventually added more functional ways to index. Another fun construct, and a very important one from a theoretical point of view, is something called defuns, which is kind of simplified functions. And this is part of the goal that my friend, my former friend, because he died a year or two in the last year or two, John Scholes, he was one of the developers of APL before he came to Dialog, and was with Dialog as long as I was, as I'd learned of their existence, that is. I never worked for them. And he was one of a number of people who was pursuing this holy grail of simplified functions that act as functional programming, which partly means no side effects and also means that you can store that the function is a full-fledged citizen that can be treated in many ways like a variable can. So I'll give you one example of a simple defun. Here's the syntax. You write it with these curly variables, and what's inside the variables is the function, and I've assigned it to a name of dist for distribution. Euclidean distance means the same as Pythagorean distance. And what we've got here is essentially the formula for the length of the hypotenuse. So here's explaining what I mean pictorially. Let's suppose we have a right triangle, and we label the corners with the variable names alpha and W. So the length of this side is W1 minus alpha 1. That is the first, well, let's put in the coordinates. Alpha is at position 2, 1, and omega is at position 5, 3. So the length of this side is W1 being 5, is 5 minus 2, it's 3, and this side is 2. And this math formula tells you the length of this side, or we could do it with APL this way. So we'd write this expression, and then we ask what's the value of D after doing that, and it's about that, which you may or may not recognize as being the square root of something or other, some integer. Then another, maybe a unique concept in APL, I don't know. It's an operator. Now, sometimes people use the word operator synonymously with function, but here we mean it in mathematics. It means something that is a special kind of function whose arguments can be functions as well. Like differentiation is an operation on a function. So here's how it works in APL. here's a common mathematical construct, and you can add things with this notation, and you can multiply things together with this notation. But there's infrequently other things, but not much. APL generalizes this, so there are infinitely many varieties of it. And we do that by separating the concept of over and of the function involved. So this slash separates a function as a left argument and a variable as a right argument. So the way to think of that is that these two bind and make a new function, which is equivalent to the sum function. And so the value of this is 17. Or we can do an or over. And or over applied to this vector is going to be 1 as long as there's at least one in the vector. You can write, if you wish, your own. Oh, I'm sorry, that's not there yet. Here's another completely different kind of operator, the each operator. And so we have a function called wash, and we have a vector of, let's say, 5 components, each one representing data about a finger. And we want to take some of the data from each of those fingers individually and apply the wash function to it. So that's a very economical way to write for statements a lot of the time, certainly simple for statements. It makes them easy to read. It's nice documentation. It's comfortable. There are about 12 primitive operators that Dialog has added to their system. Every year or two, iteration of a new Dialog interpreter might well have a new operator. Some of them are just wonderfully brilliant, and you wonder how you ever lived without them. And some of them are too complicated for me and most of us to learn about, to tell the truth. And if you want to, you can even define your own operator. I don't see a lot of that. Of course, I was very pleased with myself when I found a situation to actually write one, but it turned out that it was kind of not as efficient as doing something dumb and less clever. So I had an occasion once. John Scholes, I told you about him, a developer and very clever fellow in his quiet and humble way, very beloved person. And I asked him, how about a super operator, something that you use to combine with an operator to create, I don't know, let me put it this way. If there's a hierarchy, you've got a function, and then you have operators that that modify functions to make new functions. Could you have a super operator that attaches to an operator to define an extensive set of new operators? And I'm sorry I didn't write down John's ideas, but he did tell me he'd thought of that, but he'd only been able to come up with a couple of ideas over the years. One of them had to do with traversing a tree. That's all I can tell you. Speaking of John Scholes, though, I highly recommend that you Google for his hammer video. It is a terrific example of really low-key British humor. It's hilarious. Here's another operator that I like. Dot has different meanings depend on, and now by dot, I don't mean a center dot. That's just a mathematical symbol, not in, but you know what a factorial is. And it's written with the exclamation mark in mathematics. In APL, of course, we put the symbol before the function goes before the operand. And there's also a dyadic bang. Used to be people used the word bang for this symbol. I don't know if they still do. So 2 bang 5 means the number of combinations of 5 things taken 2 at a time, which is 10. And in mathematics, there's something called a dot product, which is a way of combining 2 vectors. And the same idea applies to matrix multiplication. In APL, we write it this way. And what's nice about that is we've separated now the functions that are involved, which are involved in the mathematics when we look at it, but are not explicitly said in the notation. But by having them explicitly put here in APL, thanks to the operator concept, you could use other symbols, maybe other symbols that nobody in mathematics ever particularly thought of. One of my favorites is the times dot bang inner product, which I use so often to calculate the number of ways to deal a certain bridge pattern. Let's see. So here's a hand of 13 bridge cards with 1 of the club suit, 6 cards in the diamond suit, 2 in the spade suit, and 4 in the heart suit. So I put down those numbers, 1, 6, 2, 4, so which are associated with the suits. And when you do times dot bang 13, because every suit has 13 cards, that's the number of bridge hands that have 1 club, 6 diamonds, and so on. And if you divide it by the total number of bridge hands, the ways of selecting 13 items out of 52, you get the probability that a particular hand would have that distribution. 1 hand in 510. Isn't that easy? Here's some things that I've done over the years that I found convenient and more pleasing to write in APL than would have been in C or in Algol. My first task when I got to IBM with Larry and Ken was, well, they thought that it was about time to implement the transpose function into APL. And I could see that it was going to be kind of a complicated project. By the way, the language that I was going to be using was raw what do we call it before a compiler language?
Machine code, perhaps?
Machine code, yeah. There was a word starting with A, but machine code is what I mean. So you write it in a symbolic way. You don't write a symbol 60 for plus, you write ADD. And then some computer converts that to the numbers of machine code. So that's the difference. So at least I had that tool. I could write you write in a way that does have symbols for variables and does have meaningful terms for functions, for operations. But it is rather tedious. And in order to get my bearings before I broke down assembly code, before I broke down into using assembly code, I modeled how the transpose would work in APL itself. So I wrote a maybe 15 or 20 line APL program in the primitive APL we had those days, which incidentally did not have any control structures. We had no for, we had no if. We would compute those things with APL primitives. I guess it was a matter of purity, but boy, I couldn't tell you how relieved I was when decades and decades later, I could actually use for in my APL programs. So I modeled it in APL, and then I was able to merely transcribe the APL function. And as long as I transcribed it accurately, I knew it would work. And if some subtlety that I didn't think of in the first place cropped up, I could go back to the model and debug it in the model and then fix the assembly code. Another project, I've lived in Venice Beach, which is part of LA, for quite a few years later on. And I lived in the best part of living in LA. You have to be careful where you live in LA. It's got upsides and downsides. But near the ocean, there's an area called Venice Beach, which has man-made canals. And the canals are flushed once a week by letting the water go into the ocean, so they'll clean up. And then you put the gate back up and fill the canals. But this business of draining the canals did not really flush out all the trash. I have to tell you, the canals were not just one or two straight lines. It was a network. So it had rectangles in it, rectangles of water. And I had noticed from my years of living in the canals, it was only an area of maybe from side to side or top to bottom, a 5-minute walk. But there was one spot that tended to accumulate trash. And when you emptied the canals, that trash didn't flow out with the water. It just settled right there to the sludge at the bottom, the muddy bottom of the canal, still available to be seen and ugly when you refilled with water. So I figured out, after an embarrassingly long time, how to model movement of water in this kind of canal. And that was a lot of fun. And with that, I was able to calculate where the trash would be, where would be the fixed spot in the canals, is what it turned out. And finally, when I got to the love of my life, the forensic mathematics business, about 1985 or 90, eventually I learned there's something called population genetics, which means the study of genes circulating in the population, as opposed to in one person's body or one animal's body or plant. And forensic mathematics, by that I mean applying mathematics to DNA for identification purposes, including criminal identification. And for that purpose, it's common to use the Y chromosome. I think I want to speed up a little bit. Funnily, I was doing a PhD in pure mathematics, but still there was enough busy work involved that I couldn't get it straight without checking things on a computer. And another purpose that I think APL is very well suited for, because at least because you can put together a small project very quickly. For example, so I've done a lot of simulations. One is, for example, let's suppose you have some bones from a war zone. So it's an anonymous grave with maybe a mass grave even. And you have a large number of people in the war zone, such as Bosnia, who haven't seen their young man relative, their son. So they assume he was murdered or killed in the war. So these people will give their DNA, and then you'll do a screening. Maybe you've got thousands of bones that have been dug up. And once you have a pretty good idea which body probably belongs to this family, you can then do some analysis and try to make the evidence, try to show that the evidence is very strong, so that you've definitely ID'd the bones. And one of the things that I wanted to do to that end is to figure out, well, how many relatives do I need? Can I do it with just a father? Well, most people who were used to identification, who are used to paternity stuff would think so, but it's not true when you have thousands and thousands of bones. There will be multiple fathers that could fit some of the bones, some of the skeletons. I'll go a little bit more into why, and I think I'm going to finish this talk with this story. So here is what's called a karyotype. It gives you a picture of all the chromosomes in each cell in a lot of the cells in your body. At least by weight, most of the cells. And the chromosomes come in pairs, although XY isn't exactly a pair, and Y is the little one. And schematically, Y looks like this. So it's the DNA is spread out linearly along here, and some points along here have names. By linearly, there's actually two threads, as you probably know, and the length of this chromosome is probably something like 30 or 40 million bases. A, T, those are bases. And there's a complementary rule that A is always partnered with T and C is always partnered with G. So if you have one string, you can reconstruct the other one, which is what the body does on cell division. And you're interested in certain patterns here. This happens a lot, that you have a repeating motif, AATG, 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 maybe 10 or 15 times in your Y chromosome. And I mean you personally, but your friend might have, instead of 14, might have only 10 replications. Because you see, nature has not had any motivation to be careful in copying this meaningless part of the genome. So it makes lots of mistakes, and it's always creating new identity. And therefore, you can identify people based on essentially the accumulated mistakes that their ancestors have at locations of this sort, which accounts for maybe 3% of the entire genome, this particular kind of nonsense. So at this particular site on the Y chromosome, maybe lengths of 14 to 20 occur. And probably what's in the middle, on the average, what's in the middle will be the commonest, just because of the way history creates variations. And roughly speaking, the chance that you and I have the same number of repeats at a particular location is probably 1 in 5, assuming we're both men. Now, we actually find they actually use about 15 standard locations here, but unfortunately, that doesn't mean that your discrimination ability is 5 times 5 to the 15. It's much less, because these things are stuck together. They're part of the Y chromosome, and the Y chromosome is one unit. Still, there's a lot of variation, which has happened over many years. It's estimated that every living man today, every living Y haplotype today, comes on a direct lineage from a single man about 100,000 years ago, maybe even a bit younger, since it's re-estimated since I made this slide. But this fellow had a certain Y haplotype, which he passed to 2 sons or more, and they passed along to sons. And then after a while, one of these passed along a different haplotype. A mutation happened, so it was a variant. So we have a subtree for that variant. mutation occurred. And then we get more mutation, every color. Now, sometimes you get back mutation, very rare though. Took me a long time to see exactly what's going on there. And I published a paper, and people still, the paper is 100% accepted by the people who think scientifically, but in the labs, people still don't understand how rare this is. So the result is that after today, there's a huge amount of variation. And here, so anyway, I did a lot of simulating in order to figure out what's going on. And let's look at it this way. Here, this little box stands for a Y haplotype. And the numbers stand for, each number stands for one of those 15 positions that we test. So we have 5 repeats at this position, 6 repeats at this position, and so on. This man had 2 children. They had children and so on. And after maybe there's 10 generations in between, these 2 cousins are Y haplotype identical by descent, it's said. Identical by descent means that they're the same because it's the exact same sequence of the connecting route between them. And the alternative would be, here's another grandpa. He has 2 different children who are a little bit different because there was a mutation at this position. And then this child had a mutation down to the grandparent and so on. But just by luck, there were just reverse mutations such that these cousins are identical. You'd never know it, but they're not identical by descent. They're identical only by state. So it took me quite a while to figure out the obvious way of calculating the chance of these different things happening. Part of it is that you realize that time can pretty well be reversed as far as mutation is concerned. The chance of going from here to here is pretty much the same as going backward. So I can unwind this picture, and I'll put this thing at the top and this one at the bottom. And then I just imagine what would happen if we went from here to here to here to here and so on. And exactly what I need for identity between the top and the bottom is to have canceling, that we have a simple pattern of canceling mutations. Basically an even number of adding and subtracting mutations at each locus. Of course, 0 is an even number. I'm going to skip out of that. So after I did a bunch of calculations, I was in a position to test a claim that had been published by some friends of mine, unusually statisticians that I respect, who had published a paper in which they said, see, Y is very, very difficult to work with because these Y types don't get randomly distributed in the population very well. And consequently, it's very hard to figure out how to correctly account for this mathematics. I mean, if you want to throw somebody in jail, you should be able to say how strong is the evidence, especially if you're dealing with DNA evidence and mathematical evidence, because DNA has an aura about it. If you go into a courtroom and you say the DNA matches, the jurors are going to say, oh my God, throw him in jail. But it's perfectly possible to have DNA evidence that's virtually negligible. What if I only looked at one locus? Then I'd have a coincidence that could happen easily. So you want to say how strong it is. And it's hard to do because all the people who match that, well, here's what Balding and Anderson figured out. They did a whole bunch of simulations, and they claim in their paper that typically a particular Y haplotype type belongs to only something like 50 different men, regardless of the population size, regardless of the history. So that means it's always rare. So I found a way. I mean, the math isn't particularly complicated. I mean, it's not obscure. It's just confusing to keep track of. And a good notation helps you keep track of things. So I'm simulating a growing population, or many growing populations actually, but I'm doing it by computation, whereas Anderson and Balding, did it with Monte Carlo simulations. So they could do something, they could get more statistics out of their way, but I did far more, I could explore far more deeply and be more sure of exactly what my numbers mean. So in this graph, I show a recent population, starting with one man only 3,000 years ago, has a different pattern than a population that's been around for a long time. A population, here's one of their discoveries, which I can confirm. The population size doesn't matter as long as it's reasonably large. 10,000 to 1 million, I get the same number of matching men, 40, for example. Their big discovery is that you have a plateau, but I think they exaggerated how much of a plateau you have. For relatively new populations, the number of men who match one another could be very large, meaning that the DNA evidence is weaker. Not such a big deal as they're claiming. So the moral is that was something that was confusing for me to write, but very clear once I was able to do it, and a lot of fun to be able to see what's going on. Okay, maybe I'm timing about right. Oh, well, no, not really. Okay, so I like the language. And being a one-person team is an enormous edge because there are certain types of things that you can do yourself. If I have a huge project and then I see after 3 years that I'm on the wrong path on a significant part of it, I can make a big change in the way I do that part. If I'm in a programming team, it's not like that. You have to go back up the hierarchy of bosses and so on and have meetings. This language is interpreted because it's too complicated to compile very well. But that nets to be good. Now, here's some more examples of things you have to learn, these funny symbols. These are funny symbols, and you have to find out how to type them. These are just great symbols, but still you have to learn how to type them. And these are miscellaneous symbols. I mentioned before the problem of precedence. Here's an example. This thing means this. It does not mean that you do the, I'm sorry, it means this. It does not mean you start with 10 to the power x. The language is used in a few communities, but not so popular. And here are some other things that I really enjoy, but I couldn't squeeze into this talk. So, no support. Nobody would give me money for this work. I even went to Spain and I asked Queen Isabella, but it turns out that she died 500 years ago. So thank you.
Yep. Thank you, Dr. Brenner. That was a very engaging talk. I really enjoyed learning more about your work, and I think everybody else did as well. I'm not sure if anyone else has any questions, or perhaps I should start with a question quickly. I know we're a little bit over time, so probably just one or two questions. I guess I can go since I'm not seeing anything else in the chat. I know APL has been built on a lot in more recent years with like things like J and BQN. I'm wondering if you ever like thought if you ever explore these, or if you ever thought about sort of shifting your work to those languages instead.
Oh, I had planned to mention J in this. I sort of glanced at J. What I know is that Ken, after doing all this work at Harvard and at IBM, and after me and Larry were gone to other places, he took his close friends and colleagues and his own, and a genius developer from Canada named Roger Huey, and also Ken's son, Eric, and they formed a small company, and Ken decided to do the whole thing over from scratch. Take what he'd learned about APL, what was clumsy about it, and do everything perfectly elegantly. One of the things that he decided not to do was these funny symbols, so he uses the normal keyboard for J. And with Roger and Eric Iverson around, I know from Roger that they did in some ways a brilliant job of implementing it, but I don't know how much it became a commercially viable language, how much it has interfaces to Windows, for example, pedestrian things that are important, or whether you can harness R or Python from J. So I know it's an intellectual tour de force, but I don't have expertise about it.
I have a question. To do the exploratory DNA analysis, like back in time or switching and seeing the mutations, doesn't it scale exponentially, and it does when you have to do large populations?
Well, certainly when I did my initial research for my first Y haplotype paper, yes, I was doing some simulation of individual people, and I was limited to about 100,000, I think, based on the DOS-based APL platform I was using at the time. But even with gigabytes of memory, that's going to be a limitation for some kinds of things.
But
plus time.
In your paper, you said you arrived at useful conclusions because you could compare with the statistical analysis.
Oh, that thing that I showed you here, I never published. I gave it at a conference. Is the only way I've published it. But I published a paper about fundamentally, how do you estimate the evidential power of Y haplotypes, assuming the most convenient assumptions that the people are evenly distributed, randomly distributed around the country. And even that problem was unsolved. And then another paper, which I published in 2014, which maybe I was starting to learn dialogue APL. Well, I was starting to learn dialogue APL. Anyway, it was easier. It didn't involve big masses of data.
Okay, thank you.
You're welcome.